Hello everyone, this is Mohammed Tariq Ibn Ziyad from Columbia University. Today, I will walk you through a subset of my PhD research work on hardware-software co-design for practical memory safety. Let's start by defining what memory safety is. In low-level programming languages such as C and C++, memory safety is a program property that guarantees memory objects can only be accessed between their intended bounds, during their lifetime, and given their original or compatible type. Violating any of these requirements will result in a memory corruption that can be exploited by an attacker. For example, accessing objects beyond their intended bounds is called spatial memory safety violation, such as buffer overflow. Spatial violations can be further categorized into contiguous violations and non-contiguous ones. In a contiguous memory safety violation, the attacker simply overwrites an adjacent buffer in memory, whereas in a non-contiguous violation, the attacker overwrites arbitrary locations in memory by jumping over the nearby objects. On the other hand, accessing objects beyond their lifetime is called temporal memory safety violation. Temporal violations can be further divided into multiple categories. The most notable ones are use after freeze and uninitialized reads. In use after free vulnerabilities, the programmer first creates an object and then copies the object address to a temporary pointer. Later on, the programmer deletes the object without setting the copied pointer to null. And that's how you end up with a dangling pointer that might be used to access the original object memory, causing a temporal memory safety violation. For uninitialized reads, the programmer allocates an object and starts reading from it before writing anything to it. And as a result, previous contents of the objects might be leaked, again violating memory safety. Now, no matter what memory safety vulnerability the program has, an attacker can exploit it to manipulate one of the following program assets. Program assets include program code, return addresses on the stack, function pointers and data pointers on the heap, and finally, non-pointer data, which are just regular variables. Based on what asset is being manipulated, an attacker can achieve different end results. For example, using a contiguous buffer overflow on the stack, an attacker can override the return address to point to the desired code gadgets, causing a control flow hijacking attack. Alternatively, an attacker can trigger a use after free vulnerability to write to some non-pointer data, causing a data corruption. And you can think of other combinations as well. Now, as we understood what memory safety is, the next question shall be, why is memory safety a concern? Well, recent incidents have shown us that the lack of memory safety is a very serious problem. People can be discriminated against, spied on, and targeted due to memory safety vulnerabilities. Unfortunately, this problem remains as current today as it has ever been. Just to put into context how common these vulnerabilities are, consider that 70% of all the CVEs in Microsoft products each year are memory safety related. Similarly, 70% of the high-severity security bugs in the Chromium project are memory safety problems, with half of those are use after free bugs. And you know what makes the issue of memory safety even worse? Attackers love memory safety vulnerabilities. Data about zero-day exploits that were detected in the wild from Google Project Zero shows that the overwhelming majority are memory safety bugs. So, what can we do about this? One obvious solution is to refrain from using languages that allow these errors, C and C++. Unfortunately, this is an unrealistic solution for many reasons. The first reason is performance. The C programming language offers high performance as it allows the programmer to directly interact with the underlying hardware. Alternative safe languages use automatic memory management, which typically adds extra overheads that are not acceptable, especially for real-time systems. The second reason is communication. C is more suitable for system-level code as it allows communication between different entities via memory. For example, a program can write to a memory mapped location that will be consumed externally by another device in the system. Safe languages do not guarantee this feature unless you write the whole system code using them. The third reason is maturity. Existing developer skills and the huge ecosystem of tools and libraries around C and C++ means that shifting to new languages would be a slow and long-term process. The fourth reason is completeness. Even for safe languages, the automatic memory management runtimes themselves are written in C and C++. So these runtimes may have bugs that can be exposed through programs written in memory-safe languages. The last reason is legacy code. There is a vast amount of legacy C code deployed throughout the world in operating systems, web browsers, and even simple embedded software. Such systems consist of millions of lines of C code, preventing the complete transition away from C or its variants anytime soon. So it seems that C and C++ are going to stay with us for some time. Is there anything we can do to fix their memory unsafety issue? The answer is yes. At a high level, Period work has followed three main directions: memory block listing, memory permit listing, and exploit mitigation. Let me quickly show you what each of these terms mean. Memory block listing surrounds all objects with regions of poisoned memory called red zones or tripwires. If a pointer ever goes out of bound due to a buffer overflow, for example, and accidentally accesses one of these tripwires, a program exception will be triggered. A famous example of tripwire-based approaches is Google's address sanitizer, which maintains a few bits for each byte in memory just to decode whether this byte is allocated, freed, allocated but not initialized, etc. The second approach is memory permit listing or pays and bounds. This approach explicitly stores the pays address and size information of each memory object and look up this information upon every load and store to check if the memory access is valid or not. For example, Intel MPX stores the base and size information in dedicated metadata tables that are accessed based on the pointer location in memory. We also have Cherry ICA, which increases each pointer size to include the base and size along with the pointer itself. As enforcing strict memory safety rules comes with non-negligible performance cost, hardware vendors have heavily invested in exploit mitigation techniques. Those techniques do not prevent memory safety violations. As you can see on the slide, the attacker can still use an out-of-bounds pointer to corrupt other objects. However, the attacker cannot abuse such memory corruption to do further harm, such as hijacking the control flow of the program. In other words, exploit mitigations mainly prevent the second step of the attack by only protecting valuable program assets. As a result, exploit mitigations typically come with very low performance overheads, making them more promising for real-world deployment, such as ARM's pointer authentication or PAC, which is available on current iPhones. While these three categories provide different security and performance guarantees, they all share one common theme. All of them add more features to a program to make it secure. In my PhD research work, I followed a quite different approach to achieve memory safety. My research focused on how to take advantage of existing program features and turn them into security primitives. This way, we can save on performance because the program is already doing what it is originally designed to do. To be more specific, I argue that leveraging common software trends and rethinking computer microarchitectures can efficiently circumvent the problems of traditional memory safety solutions for C and C++. To support this statement, I'm going to show you how my work on CaLiForms overcomes the limitations of period block listing techniques by reusing the dead bytes in program memory. I will then summarize NoFAT and how it leverages modern software trends to enforce memory safety. And finally, I will show you how ZeRØ mitigates all known exploits with no runtime overheads at all. Next, I will briefly explain the key insights behind each of these three techniques. Let's start with CaLiForms, or cache line formats. As I mentioned earlier, CaLiForms is a memory block listing technique. So the technical challenge is how to efficiently identify the block listed locations in a program memory. The straightforward approach is to use a single bit of metadata per every byte in memory, just to identify whether it is a block listed byte or not. That can lead to high memory and performance overheads. Alternatively, memory tagging extends the width of memory locations to fit a tag or color in which they can store the needed metadata. For example, Spark's ADI uses 4-bit tags per every cache line, and ARM's MTE uses 4-bit tags per each 16 byte in memory. Unfortunately, this solution is limited by the size of the tag. CaLiForms instead moves the necessary metadata inside the program memory. This allows CaLiForms to get away with just a single bit of metadata per cache line, highly improving performance. Okay, wait, how can CaLiForms do so? The key insight is to change how data is stored in cache lines. Let's start with an example. We refer to a cache line as normal if it has no block listed locations at all, like the one shown in the figure. Now, let's imagine a cache line with block listed locations or dead locations. In this case, one simple way to identify those block listed locations is to use a single bit of metadata for every normal byte. This is called the bit vector format, and it has the benefit of fast lookup. However, it introduces 12.5% memory overhead. In CaLiForms, we store metadata about the block listed locations within the block listed locations themselves. We first compress the regular data in one part of the cache line, then we use the other part of the cache line as a CaLiForms header in which we store the addresses of the block listed locations using some special encoding. In order to disambiguate between the CaLiFormed cache lines and the normal ones, we extend each and every cache line with an additional bit. This bit is set to 1 for CaLiFormed cache lines and is set to 0 for non-CaLiFormed ones. At the microarchitectural level, CaLiForms adds minimal changes to the caches. In the L1 cache, we use bit vector CaLiForms. That's the one with a single metadata bit per byte to guarantee fast lookup. We then use converters to switch between our cache line formats at the L1, L2 interface. Then for L2 cache and beyond, we only add one metadata bit per the whole cache line, resulting in 0.2% memory overhead. For main memory, this one bit can be stored in ECC bits if available, or we can store the CaLiForms metadata in a disjoint memory region in ZeRØ. Of course, as the size of L1 cache is small compared to L2 and main memory, the overall memory overhead is dominated by the 0.2%. But what about the performance overheads of this technique? We implement all the hardware changes of CaLiForms in Verilog. The results of our VLSI implementation show that our hardware modifications have no impact on the cache access latency and can be totally hidden within the pipeline. In terms of the software modifications cost, we evaluate 3 different insertion policies for the block listed bytes. The first policy, which we refer to as the opportunistic policy, only makes use of the naturally occurring dead bytes or paddings within a struct. For example, the ones that exist to satisfy language alignment requirements. The second insertion policy, which we refer to as the full policy, adds randomly sized tripwires between all fields of a struct. Using randomly sized tripwires is important for security to increase the chances of catching non-contiguous buffer overflows. Our third and last policy, which we refer to as the intelligent policy, adds tripwires only between those fields which are more prone to exploitation, such as arrays and function pointers. We implemented our policies using the CLang and LLVM compiler and measured their overheads on a real x86-64 machine. Our evaluation also accounts for the custom instruction used by CaLiForms. For example, in order to pass the block listed locations information from software to hardware at runtime, CaLiForms uses a new instruction called the block that is invoked during malloc and free. For emulating the effect of these block instructions on a real machine, we insert dummy store instructions that write some value to the corresponding block listed byte within the cache line. In our experiments, we used the SPEC 2006 benchmark suite with reference inputs, run all programs to completion. Here we can see the results for the opportunistic policy. The average slowdown in this case is almost 8%, as shown in the top figure. But what would happen if we use the full policy? Remember, this is the one that inserts randomly sized reports between all fields of a struct. In this case, the average slowdowns will increase to almost 14%. Finally, this slide shows the results for the intelligent policy. The average slowdowns in this case are only 1.5%. As the results show, the intelligent policy provides the best performance security trade-off as it protects the security critical fields with less than 2% performance overhead. Going back again to our taxonomy, CaLiForms provides a probabilistic protection against a wide range of memory safety violations with only 1.5% runtime overheads if only security critical fields are protected, and up to 14% if all object fields are guarded with blocklisted bytes. Now, let us move forward to the second contribution of my work, which is no fat. The name is an allusion of no-fat milk, which has fewer calories, all the goodness of milk, and none of its badness, except perhaps taste. Also, permitlisting work refers to their schemes as fat and low-fat pointers. The key observation of this work is that current software trends can be used to enhance system security. One example of such software trends is the increasing adoption of binning memory allocators. Binning memory allocators are typically used to enhance performance by maintaining memory locality. Examples for binning allocators include gmalloc, which is used in Firefox and as a default allocator on FreeBSD, the memalloc from Microsoft, and tcmalloc from Google. In order to understand how binning allocators work, let's consider a simple program which tries to allocate 12 bytes of memory by calling malloc as shown in line number 41. This call to malloc invokes a memory allocator which is supposed to allocate 12 bytes on the heap and returns the starting address to the program to continue execution. In order to accelerate the malloc functionality, binning memory allocators divide the virtual memory into different regions called bins. Each bin is used to allocate objects of a specific size. For example, allocation requests that are less than 16 bytes come from region A. Allocation requests that are greater than 16 bytes and still less than 24 bytes come from region B, and so on. As each region holds allocations of the same rounded size, given any pointer, we can derive its allocation size and base address. The allocation size is the size used in this particular region, whereas the base address is the nearest size-aligned address in the same region. I will flesh out the details of these calculations in a minute, but for now, the more important question is, how can we use this nice property to enforce memory safety? Let's explain this further by going back again to our example. Let us assume that after the memory is allocated, our program issues a store instruction to write the value A to pointer 4. With no fat, every load and store instruction will have one more operand, which we call the trusted base. This operand is propagated using the compiler from the malloc output to the store input. Now, it's fairly easy for the store instruction to verify access bounds. The steps are straightforward. The hardware first subtracts the trusted base from the address, which is pointer 1, to get the offset. Then it retrieves the size of the trusted base pointer using the binning allocator metadata. Finally, it compares the offset to the size and flags a violation if the offset is not less than the size. We also generate a random 16-bit value upon memory allocation and store it in the upper pointer base. We can then catch temporal safety violations upon memory access by simply comparing the upper bits of the address and the trusted base. So in short, we make the allocation sizes information available to the hardware to help it verify memory accesses. Now let's try to make the example a bit more complicated. We will take the pointer and pass it to another function foo via a direct call as shown in line number 49. Inside foo, we will write some value p to the x pointer of 7 as shown in line number 53. So similar to the main function, the store instruction from line 53 should use a trusted base as the operand. The question is, how can we get x pointer trusted base? Well, we can pass it explicitly as a second argument to foo, but this solution will change the function signature and break binary compatibility. Instead, we just recompute it using a comp base instruction. This instruction takes advantage of the binning memory allocators as follows. First, it gets the region of the pointer using a simple shift operation. Then it retrieves the region size from the binning allocator metadata. Finally, it computes the base by multiplying the pointer by the inverse of the size, rounding it down, and multiplying the outcome by the size again to get rid of the remainder. Now we have our new base address without passing any explicit operands between functions. One might ask the following question. What is going to happen if a pointer arithmetic operation in the main function pushes the pointer out of bounds before passing it to foo? In this case, foo will receive an out of bounds pointer and will compute a wrong trusted base. To avoid such problematic situations, we always verify the bounds of all pointers that escape to memory or to another function by using a verify bounds instruction. If the pointer is already out of bounds, we flag a violation at line number 44, and it will not be passed to foo. If the pointer is in bounds, we are guaranteed that foo will receive a valid input. At the microarchitectural level, NoFat requires minimal modifications. First of all, NoFat does not use per cache line metadata. As a result, no changes to the memory subsystem are required at all. Instead, NoFat changes are internal to the core. For example, in order to make allocation sizes available to the hardware, we use a 1 kilobyte memory allocation sizes table or mast to keep track of the allocation sizes used by the memory allocator in different regions. This way, we avoid accessing the allocator metadata to retrieve the region size for every memory access. As the size of this table is small, it's easily swiped out and in upon process context switch. Next, NoFat uses a bound checker to validate all memory accesses, as I described before. Finally, NoFat uses a dedicated register file for base addresses, just to avoid adding register pressure on the regular register file. In terms of performance evaluation, we measured the overheads of NoFat for the SPEC 2017 benchmark suite on a real machine by replacing our instruction set extensions with dummy instructions and using a simple binning memory allocator. As shown in the top figure, NoFat reduces the average performance cost of memory safety from 100% in case of software base and bounds to just 8%. If we zoom in a little bit, we can see that most of the NoFat's overheads are attributed to our simple binning allocator, which introduces 4% runtime overheads compared to the baseline, in addition to the overheads of the back-to-back multiplications that are used during base address computation. So, using a different binning allocator like Microsoft Me-malloc and a small hardware cache for saving the base addresses of frequently accessed derived pointers reduces the NoFat runtime costs to less than 1%. So, in short, NoFat provides spatial memory safety and a degree of temporal memory safety with negligible runtime overheads when a binning allocator is used. So far, we have seen how my work advances memory block listing and permit listing. Before moving forward to the last part of this talk, let us take a couple of minutes just to see how my first two techniques compare to prior work in the field. This table summarizes the main approaches for achieving memory safety in the first column and the metadata used by each approach and its security coverage in the other two columns. Starting with memory tagging techniques like ARM MTE and Spark ADI, those techniques assign colors or tags to every memory allocation and store the color in the pointer upper bits. Unfortunately, the security coverage of memory tagging is limited by the tag width, which is typically 4 bits. On the other hand, barrier tripwires-based solutions like address sanitizer avoid the pair pointer metadata and attach them to the allocation itself. Unfortunately, traditional tripwire systems are susceptible to non-adjacent buffer overflows. CaLiForms overcome this limitation by using random-size, fine-grained tripwires to make it harder for attackers to jump over them using a non-adjacent overflow. Finally, explicit base and bound techniques such as Sherry increase pointer widths by extra bits to store the allocation bounds information. While such techniques provide high security coverage, the additional pair pointer metadata makes pointer operations more expensive and breaks compatibility with the rest of the system. In contrast, our permit listing solution, NoFed, has a fixed size metadata table per the entire process, just to store the allocation size used by each pane, while maintaining strong security against adjacent and non-adjacent overflows when a pinning allocator is used. With that being said, let's now move on to ZeRØ. ZeRØ, which stands for Zero Overhead Resilient Operation Under Pointer Integrity Attacks, is an exploit mitigation technique. To be precise, ZeRØ protects pointers such as return addresses, function pointers, and data pointers as they represent the main target for memory safety attacks. So, how does ZeRØ work? Let's again start with a simple example. This program has an instruction to the left, memory contents on the right. When a function is called, the return address, for example, program counter +4, is typically pushed to memory. Later on, when function finishes execution, the return instruction loads the return address from memory and jumps to it. In other words, a return address is a code pointer. So what can go wrong in this case? Well, attackers can use a buffer overflow to store their own address to the return address in memory. Now, when the return instruction is executed, the program will move to the attacker-controlled address instead of the original program counter +4. That's a well-known attack vector called ROP, or return-oriented programming. To protect the return addresses, we simply tag every return address upon a call and verify the tag upon a return. If a store instruction is used to overwrite the return address, ZeRØ will reject this instruction to protect the return address. We also raise an advisory exception to notify the operating system, so it can log the attack for forensics without actually crashing the running process. This way, we achieve resilient operation under pointer integrity attacks. Similarly, ZeRØ protects function pointers by using special load and store instructions to access them. For example, function pointers are read into memory by code pointer store instructions and are read using code pointer load instructions. This way, regular store instructions from a buffer overflow, for example, cannot be used to corrupt function pointers. The same idea is also applied to data pointers. In other words, data pointers are only accessed by data pointer load and data pointer store instructions. So far, I have been talking about tagging different program assets while being stored in memory. So I think it's fair to ask, how can ZeRØ keep track of these tags bits in memory? In other words, how can ZeRØ efficiently identify if a memory word is a return address, code pointer, data pointer, or simply regular data? In ZeRØ, we store metadata about the program pointers within the pointers themselves. This is feasible on 64-bit systems as the top 16-bit of all pointers are unused anyways. Unused bits means some sort of dead bytes. Dead bytes means CaLiForms. So we invent a different variant of CaLiForms in which we use some of the upper pointer bits in each cache line to craft a header that identifies both the locations of the pointers within the cache line and their type. Similar to CaLiForms, ZeRØ has no impact on the cache access latency. At the software level, ZeRØ special load and store instructions use the same number of registers as regular load and stores, basically introducing no changes to the binary size. The only exception is our clear meta instructions, which are used to clear the metadata bits upon object deallocation or deletion. For emulating the effect of these clear meta instructions, we use a compiler pass to insert dummy store instructions that write some value to the corresponding upper pointer bits in the cache line. As clear meta instructions are uncommon, the performance overheads of adding ZeRØ to the SPEC 2017 benchmark suite are true to its name, 0% on average, as shown in the top figure. ARM pointer authentication, or PAC, which is now found in iPhone devices, is the closest commercial competitor and provides strictly weaker guarantees than ZeRØ. We emulate the performance overheads of ARM PAC for protecting function pointers in memory by using dummy instructions on an x86 64-bit machine. The average slowdown in this case is 3%. Using the ARM technique to protect the more common return addresses incurs 6% runtime overheads on average. Whereas applying ARM PAC to its full extent to protect all code and data pointers increases its overheads to 14% on average. Practically speaking, the main source of runtime overheads of PAC is the extra invocations of the crypto operations for each pointer. Every time a pointer is stored to memory, a hash should be computed using Karma cipher and stored in the pointer upper bits. When the pointer is loaded from memory, a new hash is computed and compared against the stored one. So, as ZeRØ does not require any crypto operations, it reduces the average runtime overheads of pointer integrity from 14% in case of ARM PAC to 0%. So, in a nutshell, ZeRØ provides an efficient pointer integrity mechanism, which is easy to implement, has no runtime overheads, and provides strong security. Thus, it can serve as a drop-in replacement for ARM PAC with better guarantees and with zero overheads. And that's how we fix the memory unsafety problem in C and C++. By blocklisting accesses to dead memory regions using CaLiForms, permitlisting valid memory accesses with no FAT, and protecting important program assets such as pointers with ZeRØ. Obviously, none of these projects would have been possible without the help of my great collaborators. So I'd like to say thank you for all of them. I consider myself very lucky for having the chance to work with you all during my PhD, especially my advisor, who inspired me to work on memory safety and gave me endless support over the past 5 years. If you have made it this far, thank you so much for listening. For more information, please check out the material on my website. And if you have any questions or comments, please do not hesitate to reach out to me via email or Twitter. Thank you.